It's 9:01, so good morning, everybody, or afternoon, or evening, wherever you're located. I'm Patrick Brady. I'm the spokesperson for the LIGO Scientific Collaboration. I want to welcome you to another one of our webinars and to introduce the moderator for today's presentations, which is John Veach. So with that, I'm simply going to hand it directly over to him, and he and the speakers will take it away. John.
Thank you, Patrick. I hope everyone can hear me okay. So before we get started, I wanted to run over the way that we'll be running the webinar with the participants. So there will be time for questions at the end. I would ask that you type your question into the Q&A box, and I will see that pop up, and I'll make sure that I can direct that to the correct person at the end of the presentation. And before we get going, there's a few pieces of information on this title slide. If you don't want to copy these URLs down, then you can simply go to the presentation slides themselves at the link down here, and that will help you also if you have trouble seeing the video. You can follow along on your own desktop. Furthermore, there are a couple of other webinars that are planned for the next 2 weeks as well, and we'll talk about what will be in them later on. But first of all, I'd like to just give us an introduction to why we're giving this webinar today. And that's because we've just finished the analysis of the first half of the third observing run of Advanced LIGO and Advanced Virgo. So the reason that we're so excited about this could really be summed up in this very simple animation. If you look here, there is a diagram of all the neutron stars and black holes that we know about in our galaxy, superimposed with those that LIGO and Virgo detected during the first observing run. We can then fast forward to the second observing run. Oh, sorry, the video. If we fast forward to the second observing run, we'll see the addition of another 10 objects. And finally, with O3, you can see this huge explosion in the number of signals that we've been able to detect. So today we'll be looking at some of the implications of those, the results that we found, what we've seen, but also a bit about the instruments that have made these detections. So we have a series of panelists. Ilaria from the University of Rome will be talking about the actual instruments, Advanced LIGO and Advanced Virgo, and how they're performing at the moment. Derek from the LIGO lab at Caltech will be talking us through how the observing run went, how the instruments were performing. Sarah will be telling us about the searching and detections and what we actually have identified as new gravitational waves. And finally, Zohair will talk us through what it is that we've seen and tell us about the properties of these signals. And finally, at the bottom is myself, the moderator. And if you have questions, I'll be keeping an eye out for them. So we might as well get started, and I'll turn you over to Ilaria, first of all, to talk about aspects of the instrument science. Take it away.
Okay, thank you, John. Hi all. In my part, I will describe all the upgrades that have been implemented in each gravitational wave detector during the time break between 2 and 3A observing runs. So next slide, please. Thank you. Ground-based interferometers are the best gravitational wave hunter in the range 10 Hz, 10 kHz. They are Michelson interferometer operating at the dark fringe with Fabry-Perot optical cavities in the arms. Each Fabry-Perot cavity is formed by adding an input mirror to the simple Michelson interferometer. They are spherical mirrors made by high-purity fused silica. Their diameter is 35 centimeters. Their mass is around 30 kilograms. And each mirror is suspended by 4 fibers whose thickness is around 400 microns. Here there is an image of the naked mirror, while here in this image you can see the mirror that is suspended and integrated inside the detector. Next slide, please. Okay, each detector is characterized by its sensitivity curve, that is an identity chart of each gravitational wave detector. obtained by summing all noises that are present inside the detector. We identify three different range areas depending on the frequency. We have in the low frequency range, the most important contribution is due to the thermal noise, due to the suspension system of the mirror. In a very few simple words, the thermal noise is a feature of all bodies at thermal equilibrium. And this is caused by the thermal vibration of the particles that at a macroscopic level generates an effect, changing the position of the mirror, mimic in this way the effect of the passage of gravitational wave. Next slide, please. In the medium frequency range, the most important contribution to the noise is the mirror thermal noise. So next slide. And finally, there is the quantum noise that covers all the frequency range of detection. In particular, the quantum noise is given by two different contributions. At a low frequency, the dominant noise, the radiation pressure. Also in this case, we have a displacement noise because the photons hit the mirror, changing again the position of the mirror and mimic the effect of the gravitational wave passage. At high frequency, the higher noise is the shot noise. That is, in this case, that is different from the thermal noise or radiation pressure because it is a readout noise due to the fluctuation of the photon number detected by the photodiode. The radiation pressure is proportional to the circulating power in the detector, while the shot noise is inversely proportional to the circulating power in the detector. So next slide, please. So by summing all these noises, we obtain the sensitivity curve that indicates the minimum detectable gravitational wave signal. This means that all the signals that are above this curve can be detectable, while all the signals that are below this curve cannot be detected because they are covered by the noise. In the left plot, there is the final sensitivity curve concerning the design, so it is theoretical, while on the right plot, you can see the real life. This is an example of a measured sensitivity curve. You can see all peaks that are present inside the curve. They are due to the technical noises related to the real implementation of the instruments. So next slide, please. The gravitational wave detectors network is now formed by 3 interferometers, the 2 American ones, LIGO Hanford in Washington, LIGO Livingston in Louisiana, and the European Gravitational Observatory Virgo located in Italy near Pisa. The next will be KAGRA in Japan. Next slide, please. So now we can analyze in details all the upgrades that have been implemented in each gravitational wave detector. Let's start with LIGO Livingston. Concerning the low frequency region, during the past science run, it has been discovered an extra noises, probably due to the static charge of the mirror. For this reason, a complex discharging system has been implemented and installed in the detector. This noise has been reduced, but it is not completely disappeared. And so this is an open issue that must be investigated and solved. Concerning the high frequency, the big improvement at high frequency has been reached by reducing the quantum noise. 2 different strategies have been adopted to reach the goal. The first one was to increase the circulating power in the detector. So the input power of the main laser has been increased from 25 watts to 30 watts. And also the end mirrors of each Fabry-Perot optical cavity has been replaced with another one characterized by power scattering losses. The second approach that has been followed to reduce the quantum noise was to inject the squeezed light in the detector. The squeezing technique is an application of the quantum optics. In this field, light is represented by two different quadratures, phase and amplitude. And considering the Heisenberg uncertainty principle, we can reduce the uncertainty in the phase quadrature or amplitude quadrature, obviously at the expense of the other one. So in our case, we squeezed the phase quadrature, and in this way we were able to reduce the shot noise. So next slide, please. Concerning LIGO-Hanford, the same upgrades have been installed in this interferometer, but also an input test mass of one Fabry-Perot cavity has been replaced due to the presence of some imperfections on its surface. Next slide, please. Finally, concerning Virgo, the big improvement in the low frequency was achieved by reducing the thermal noise. In fact, we installed the fused silica suspension to suspend the mirror. And also at the same time, the vacuum system has been upgraded to reduce the dust contamination risk for the fibers. At medium frequency, the improvement in the sensitivity has been reached thanks to the reduction of the electronic noise. It is a typical technical noise by installing high quantum efficiency photodiodes on the dark port of the detector. At high frequency, the improvement in the sensitivity has been reached by following exactly the same strategy of our LIGO colleagues. Also in this case, the quantum noise has been reduced by increasing the circulating power in the detector. In particular, the input power has been doubled from 10 watts to 20 watts. And also, we injected squeezed light in the detector to reduce the shot noise. That's all for me. Now, Derek, we will talk about operations and data taking.
Thank you very much, Ilaria. So yes, I'm going to be talking now about operations and data taking during the last observing run 03A. And here we'll be able to really see how all of the improvements that Ilaria just introduced have led to significant increases in our ability to detect and analyze gravitational wave signals. So next slide, please. So taking the complex sensitivity curves that Ilaria introduced, we can condense this down to a single number to describe the detector sensitivity, which we refer to as the binary neutron star range. Now, this is the average distance averaged over the entire sky that we would be able to observe gravitational waves from a binary neutron star merger at around a signal to noise ratio of 8. This is where we can start to differentiate a real gravitational wave signal from background noise. Looking at how the detectors performed during 03A, on the right, we can see that the median range for each detector is 135 megaparsecs for LIGO Livingston, 108 megaparsecs for LIGO Hanford, and 45 megaparsecs for Virgo. On the left, we show this range number throughout the entirety of 03A, and we can see that for the most part, the detectors were fairly stable. There's variations on the order of around 10 megaparsecs, both long-term and short-term. These long-term variations are generally dominated by slight changes to the instrumentation over the course of the run, while short-term changes are more about changes to the environment, just storm activity or day-night cycles. Next slide, please. And taking these sensitive range numbers, the sensitivity of our instruments, we can try to compare against where we were in the previous observing run 02 to really nail down how exactly we've improved. So on the left, I'm showing the exact same numbers now compared against our values from 02. And we can see at LIGO Livingston and LIGO Hanford, there's been roughly an increase of about 50% in the binary neutron star range, which is really significant. But at Virgo, there's almost a doubling of this range, which really speaks to the broadband improvements at the Virgo detector. Now, while we do use the binary neutron star range to quantify our sensitivity, if we really want to figure out exactly how this translates into number of gravitational wave detections, the number we really want to think about is the sensitive volume, because we're surveying space to see these gravitational wave signals. So if I take the same values that I've plotted here on the left for our sensitive distance and try to figure out what is the volume of a sphere that has a radius of that distance, I get the values on the right. And as you might expect, this is showing even much larger increases in our sensitivity. LIGO Livingston, LIGO Hanford, there's a factor of 3 to 4 increase, while Virgo is almost a factor of 8. And this is going to be really good to keep in mind when we start to talk about the large number of gravitational wave signals that we've detected in this observing run. Really, this kind of is the best example of why we would expect this to happen. Next slide, please. In addition to having an extremely sensitive detector, we also want to be operating each of our detectors as much as possible to be sensitive to as many gravitational waves as we can. The two numbers we use to quantify this are the duty factor and uptime, where the duty factor is just the percentage of time that each detector is observing, and the uptime is the total amount of time. Now, if we compare the values that I've shown here for O3A and O2, we can see that there's some significant increases in the duty factor at each site here in O3A, which again is mostly due to these detector improvements that Ilaria was describing that have increased the stability of our detectors. We now can ride out and continue operating through even more severe environmental conditions than we were in previous observing runs. But not only do we care about the individual detector duty factors, but we really care about this network duty factor, because we are a gravitational wave interferometer network now. And looking at this plot on the right, I've split this down the whole 6 months into time periods where either 3, 2, or 1 interferometer operating. We had all 3 interferometers operating about 45% of the time, which is really important for us in order to make detections, and even more importantly, to have precise sky localizations allowing for electromagnetic follow-up of our signals. We also had 37% of the time where 2 interferometers were operating, and 15% of the time where only 1 interferometer was operating. But combined across all 3 possible combinations here, that means there's only about 3% of that entire 6-month period where we didn't have a single detector operating, and we wouldn't have been able to detect any gravitational waves during that time period. So we have almost complete coverage of the entire 6 months. Next slide, please. Now, in addition to these somewhat idealized metrics of how sensitive we might be to gravitational waves, there's a lot of additional complications that might happen in our data that could limit our ability not only to see a gravitational wave, but to be able to confidently identify it in all of our data that we have available. So for our short duration bursts of gravitational waves that are characteristic of the compact binary mergers, one of the biggest problems is short duration instrumental artifacts that can create excess noise in our detectors that can limit our sensitivity to these other real gravitational waves. Now, some common sources of glitches include things like scattered laser light that's reflected off of the test masses and gets bounces off something in the detector and gets recombined into the main laser beam, but also things like thunderclaps or earthquakes, which could shake the entire detector all at once. On the right here, I'm showing an example, very unfortunate, in fact, of a case where there was a glitch directly overlapping one of our signals. So in orange, in both the top and the bottom panel, is plotted the in-spiral track, so basically the time frequency evolution of our gravitational wave signal. And we can see there's a significant amount of power at lower frequencies in an arch shape that doesn't follow this track. So this is a glitch due to scattered light at the same time period as the signal. Now, in cases like this, when there is an impact of these glitches on our gravitational wave signals, we do our best to model and subtract these glitches using the Bayes wave algorithm before sending it to parameter estimation. So unfortunately, glitches are a fairly significant problem in gravitational wave detectors, and about 20% of our total number of signals did have to require some type of mitigation to deal with data quality issues. Next slide, please. Looking at the performance of the detectors in respect to glitches over the entire course of the run, we do see quite a bit of variability at each site. So overall, during O3A, the median rate of glitches is higher than in our previous observing run at both of the LIGO Hanford and LIGO Livingston site. This is partially attributed to the increase in sensitivity of the detectors. But at Virgo, there's an over an order of magnitude increase or decrease, sorry, in the glitch rate as compared to O2, which really I think shows how much more stable and sensitive that the Virgo interferometer is. There are some short-term variations of about an order of magnitude in the glitch rate at all three sites, which generally are due to environmental conditions, but also could be attributed to short-term duration instrumental issues. So if there may be some new source of instrumental noise in the detector, which we can hopefully quickly identify and resolve. So this is, I think, the biggest, really the biggest reason for a lot of the changes that we're seeing in this plot. One kind of interesting example of something that we were able to resolve during the course of the run at LIGO Hanford was that it was discovered that there was a camera in one of the end stations near the vacuum chambers that was taking photographs every 2 minutes or so, and the shutter going off was enough to shake the mirrors just enough for it to show up in our detectors. So turning it off resolved the problem, made our data quality better. Next slide, please. And then also really important for us to make precise gravitational wave measurements is the calibration of interferometers. So there's two aspects of interferometer calibration. The first is trying to model and understand the response of the interferometer, which is called the sensing function. This is basically what data do we record when the arms are stretched and squeezed. But we also need to really well understand how the force that we apply to test masses to keep the interferometer stable also impacts the data that we record. So if we let our test masses freely swing, we wouldn't be able to keep the interferometer locked in a very stable operating state. So we do have to push on the mirrors a bit to keep them operating, but we do record this and model this very well in order to get an accurate measurement of the physical strain that we record. One of the ways that we do this is with a photon calibrator, which is a laser that actually pushes on our test masses with a known force. And we use this as an absolute reference at all three interferometers. And then finally, once we've calibrated the data, there's additional measurements that we complete of the interferometer and evaluating the data that's been produced to try to understand any residual systematic uncertainty that might have not been included in the original calibration model. This type of calibration is really important for all the precise parameter estimation that we do, especially for things that are amplitude dependent, such as figuring out the distance to a gravitational wave signal. Next slide, please. And then finally, I want to talk about gravitational wave event validation. So as you just saw, there's this quite large number of these glitches and other type of challenges that we might encounter while completing gravitational wave detection. So one way we try to address this is by using a large array of sensors throughout the site. There's on the order of a few 100,000 different sensors across each interferometer site that are used to monitor the environment, the performance of the detectors. So on the right, I'm showing one example of the sensor array at LIGO Livingston. So this is the Physical Environmental Monitoring Sensor Array, short PEM for short. And this includes things like accelerometers all over the site that are trying to measure any type of shaking that's happening, to things like wind gauges, temperature, microphones, even cosmic ray detectors. So really, if there's anything happening at any of our interferometer sites, we want to know about it. And using all of this additional information, we investigate if there's any evidence that any of our candidate gravitational wave signals is actually due to a glitch or some other type of detector issues instead of a real gravitational wave signal. And based on these investigations, no candidates GWTC2, this catalog, were confidently identified as not astrophysical based on these investigations. So there's no identified issues with any of our candidates so far. And with that, I'll turn it over next to Sarah, who's going to be talking a bit about our search and detection process.
Thanks, Derek. Yeah, so as you just heard from Ilaria and Derek, advanced LIGO and Virgo have had significant increases in sensitivity due to the hard work to upgrade the detectors between the second and third observing runs. So on the next slide, we can see that this has enabled us to increase the number of confident gravitational wave detections by more than 3-fold over the first gravitational wave transient catalog. The analysis of O3A data has resulted in 39 new gravitational wave events. And if we add this to the 3 detections from O1 and the 8 detections from O2, this brings our total to 50. gravitational wave events that have been detected since we started September 2015. So given the increased sensitivity, these 39 events found in this 26 weeks of data of O3A are consistent with the number of detections in our previous catalog, GWTC1. Okay, next slide. So we identify gravitational wave candidates on 2 timescales. First, there's low latency, where identification happens seconds to minutes after the signal has arrived at Earth. And second, there's offline, where identification happens days to months later with a reanalysis of the data. And here we often have improved template banks, updated calibration, data quality vetoes, and other developments that make it possible to find additional and often weaker signals in the data. So in low latency, we had 5 detection pipelines running. There's Coherent Waveverse, which was an unmodeled search, and GST-Lao, PyCBC, MBTA Online, and SPEAR, which are modeled searches. So I'll say more about this in a minute. These pipelines detected 33 candidate events in low latency that were rapidly communicated through the GCN notices and circulars. Of these 33, 7 low latency candidates were actually not confirmed by the offline reanalysis, but 26 did survive, so 26 of these candidates were confirmed. And also, offline reanalysis with Coherent Waveburst, GST-Lao, and PyCBC identified 13 additional candidates that are reported in this catalog for the first time. Okay, next slide. So this catalog, of course, is reporting on gravitational wave discoveries from compact binary coalescences. These binaries are composed of stellar mass neutron stars and black holes or combination systems. And modeled searches for these types of gravitational waves rely, of course, on the model of the signal. And that model is dependent on the source's physical parameters. So the most important parameters for understanding the phase evolution of the waveform that we see at the bottom here are the component masses, mass 1, mass 2, and the component spin angular momentum. So here I've labeled a spin vector that we call chi1 and chi2. For searches, we're interested in this quantity called the effective spin, which is defined there. It's basically a mass-weighted combination of the component spin, chi1 and chi2, that's either aligned or anti-aligned with the orbital angular momentum. So of course, once we've made a detection, it's very interesting to try to measure these masses and spins, and you'll hear more about that in the next section. But on the right, you can see the mass and spin parameters of the waveform templates that we used for match filtering and searches, such as GST-Lao and PyCBC. In general, the masses are from about 1 to several hundred solar masses that we're covering. And we're currently here only searching for systems that have the component spins aligned or anti-aligned with the binary's orbital angular momentum. Okay, next slide. Now we also had an unmodeled search running because gravitational waves from compact binary coalescences can also be recovered by unmodeled searches. The offline results from one unmodeled search were included. This was Coherent Waveburst. And instead of a specific waveform model, Coherent Waveburst performs a search on time frequency data obtained with the wavelet transformation, like that shown on the plot on the right. So in this way, you can see the characteristic chirp signal from the compact binaries that can be detected. Coherent Waveburst has the highest sensitivity for short duration, high mass signals, and its sensitivity will decrease for the lower mass systems with the longer duration waveforms. And we also note here that CWB, Coherent Waveburst, required candidate events to be found in coincidence between at least 2 detectors. And so you'll see in the paper, table 4, Coherent Waveburst recovers fewer candidates than the other searches. Okay, next slide. So beyond the initial trigger from the match filter or the power in the time frequency domain, each search pipeline actually employs a series of additional steps that better enable us to distinguish real gravitational wave signals from false alarms. So these steps could include including a time delay or a phase offset check between triggers in the different detectors, tests against expected signal or noise morphology, inclusion of data quality like Derek mentioned, as well as other statistical tools. And all of this information is then used to construct a multivariate ranking statistic by each search for each candidate. In O3, so not only are the detectors better, but our search algorithms and the construction of these ranking statistics are also better. For example, the GST-LAL pipeline analyzed for the first time single detector candidates along with double and triple detector candidates. And so as we saw from Derek's slide, single interferometer time is 15% of O3A. So it was very, very important to search this data if we could. Additionally, PyCBC included results from a binary black hole focused search, and both searches include improvements to the ranking statistics. Okay, next slide. So 39 gravitational wave candidate events passed our false alarm rate threshold of 2 per year to be included in GWTC2. And given the multiple pipelines, this means that we could have up to 3 false alarms mixed in our event list. In other words, these would be candidates caused by instrumental noise. It's not possible to determine which, if any, candidates are caused by noise, but we do provide statistical measures of the false alarm rate and probability of astrophysical origin for each candidate to guide us in the significance of that candidate. So the false alarm rate, shown on the left here, is computed by each search by computing the number of background events that yield a candidate with a ranking statistic, here that I've arbitrarily called lambda, higher than some lambda threshold. And this is over some experimental length t. And then we also, for each candidate, we compute the probability of origin from an astrophysical source, p-astro. In the catalog, you'll see that we only consider p-astro for events that are consistent with a binary black hole origin via this Poisson mixture model formalism. So you can read more about that method in the paper referenced here if you'd like. So these are the 2 quantities that you'll see in the table on the next slide. This is table 4 from the paper. So these are the results from the Coherent Waveburst, GST-LAL, and PyCBC offline reanalyses that passed a FAR threshold of 2 per year. And unlike GWTC1, p-astro cut was not additionally applied to the candidates here. But you do note that p-astro is greater than 50% for all the candidates in the table. The names that are listed here are basically encoding the UTC date with the time of the event given after the underscore. But you'll notice that there are a couple exceptions. So GW 190521, 190425, 190412, and 190814, which were previously published with these names, so they don't have the underscore. Candidates highlighted in red are the most likely to be noise, although as I said, we expect fewer than about 3 candidates in this list to actually be noise. The candidate with the highest false alarm rate is 190426, which was previously reported in low latency as a possible neutron star black hole event. But because of the high false alarm rate, we should treat this candidate cautiously. The candidates marked with a green X are the 13 previously unreported events that were identified only in the offline reanalysis. And again, as I mentioned, having recovered candidates in single detector time is new for this catalog. So these are the candidates highlighted in yellow. And allowing for single detector candidates allows us to report on additional astrophysically interesting candidates, but it does remove the powerful check on coincident background. So there are larger uncertainties associated with the false alarms for these candidates. So again, treat these cautiously. Okay, so I will now turn it over to Zohair to talk to you about the details of these candidates.
Thanks, Sarah. All right, let's go to the next slide. So Sarah was telling you about all the gravitational waves that we've detected. And now we want to know what sources created those gravitational waves to begin with. What was the nature of the 2 objects that we saw inspiraling and merging? So to make that inference, we use Bayesian inference. And so at the top of this slide, I've written Bayes' rule. So on the left-hand side of this equation, we have the posterior distribution on the source parameters given the data. The source parameters we want to know are things like the masses of the 2 objects, the spins of the 2 objects, their distance away, sky position. we're able to condition these inferences on the data, which is just the strain in all of our operating detectors at the time of the detection. So we can rewrite the posterior in terms of a likelihood and a prior. For the likelihood, we take it to be Gaussian in the residuals between the strain data and a choice of model and parameters to that model. And then we also need to set priors on all of the source parameters that we're trying to infer here. We take the same prior choices that we've used in the past, which is uniform in detector frame masses, uniform in dimensionless spin magnitude, isotropic in spin orientations. The one place where we make a slight change to our prior compared to our previous publications is in the distance. Before we used a luminosity distance squared prior, and now we want a prior that has a constant rate in the co-moving frame. So that's one change from our previous publications. All right, next slide, please. So as I mentioned in the last slide, we have that likelihood that we need to calculate, and that requires us to actually use some model for what the gravitational waves should look like in the detectors. So we use a number of waveform models. I'm not going to go through all of them that are shown here, but I do want to say that there's a lot of different physics that we have in these different models. So we have some where there's no spins on the two colliding objects. There are some models where there is spin, but the spins are only aligned with the orbital angular momentum. We have some with precessing spins, where the spins can be misaligned from the orbital angular momentum. And we have waveform models that include higher modes. So we have all of these different effects that we've tried to model. So you can hear more about what models we used in the testing general relativity webinar that we'll have in the next week or two that will be advertised. All right, next slide, please. So we use those models to make inferences on the masses and spins and other source parameters for every single one of these events in this updated catalog. In particular, we are able to estimate these posterior distributions using posterior samples. We draw these posterior samples using Lau inference, Bilby, and Rift samplers. Now, as I said, we have used a lot of different models, but in the actual paper, in the numbers that you see and the plots that you see, we have to choose a fiducial set of results to show. So what we've done there is we combine posteriors from runs that have similar physics, and we show the results from these combined posteriors. If we see a difference between the posteriors for the non-higher mode runs and the higher mode runs, we'll always choose the higher mode runs. And pretty much all of these runs that you've seen, they use the precessing waveform. So the spins are allowed to be misaligned from the orbital angular momentum. And the last thing I want to emphasize is that all of these inferences that we've done are public and available to you through our data release. So we encourage you to check that out. All right, next slide, please. Not sure if we've lost John. All right. I guess I can screen share if John has gone. Can people still hear me?
Yes, so here we can hear you.
Great. I'll go ahead and pull up the slides then. It seems we have John back. John, do you have the slides? All right, I'm not hearing from John, so I'm just going to go ahead and share them myself. Oh, there we go. Thanks, John. Yeah, can you go on to the next slide? All right, so here's a plot showing the 90% contour. So these are contours that enclose 90% of our posterior belief on some of the source parameters for all of our events. In this plot in particular, we're showing the plane of mass ratio and total mass. So the mass ratio is M2 divided by M1. So that's the mass of the secondary divided by the mass of the primary. We always assume that the label 1 is labeling the more massive object. So towards the top of this plot, that's a region where the mass ratio is very equal. So M2 would be very close to equal to M1. And towards the bottom of the plot, that's when you'd have an unequal mass for these two colliding objects. And then on the x-axis towards the left, there's the low total masses. And then to the right-hand side, we have higher total masses. All right, next slide, please. So let's dig into this plot a little bit more. I want to highlight a few events. Firstly, GW190425. So both components of this system have masses less than 3 solar masses, which is consistent with a binary neutron star merger. And that's why you see it in the top left of this plot on the left-hand side of that M1 equals 3 solar masses line. This has been published before, so you've seen it. Next is GW190426, 152155. As Sarah mentioned, this is the highest false alarm rate event. It's low significance, but nevertheless, we can still run our parameter estimation routines on the data. And we find that one component has a mass less than 3 solar masses. So this would make it consistent with a neutron star black hole merger, but again, it's low significance. The next event I want to highlight is GW190924021846. This event is interesting because of all of the events where the secondary mass is greater than 3 solar masses, this is the lowest total mass system and likely has the lowest component mass. So this event is just interesting because it's starting to fill in what the population of black hole mergers will look like near the 3 solar mass line. All right, the next event is GW190814. This is another event that was previously published. This one, again, was interesting because one of the components was less than 3 solar masses, although we weren't able to say confidently exactly what that was. Another interesting thing about this system is that the spin of the more massive object in it was very well constrained to be very close to 0 or 0. Next, I want to highlight GW190412. This one was a confidently unequal mass merger where both components were greater than 3 solar masses. And even though it has a very strong constraint on the mass ratio and constrains it away from being equal mass, we can't say for sure that it has the most unequal mass because you can see these gray contours reaching down to the bottom of that plot. And so the uncertainties on the other events make it so that we can't say confidently that 190412 had the most unequal masses where both masses were greater than 3 solar masses. And then lastly, GW190521, this is again an event that was published before you've seen. And this is likely from the most massive system that we've seen and most massive component black hole. All right, next slide, please. I want to quickly highlight that we have done some additional parameter estimation runs on GW190425, which was published almost a year ago now. And so we encourage people to go and dig into those results in our data release. The punchline is that those results are very consistent with the results that we had initially gotten with our IMR phenom models. All right, next slide, please. Okay, I'm showing contours again in this plot, similar to the one that we saw a couple slides ago, except this time on the y-axis, we have the effective in-spiral spin, and on the x-axis, we have the chirp mass. The effective in-spiral spin is a measure of essentially the mass-weighted component of the spins that's aligned with the orbital angular momentum. So if chi effective is very large, then the spins are large and aligned with the orbital angular momentum. If it's negative, very negative, then they're large and anti-aligned with the orbital angular momentum. And the chirp mass is this combination of M1 and M2 shown at the top. And the thing I want to highlight in particular is that there's a few events we're seeing where their chi effectives are inferred to be non-zero, in particular positive. So John, if you click one more time, we'll see that GW19, there were about 10 sources, sorry, that had a positive effective in-spiral spin at 95% credibility. In particular, GW190517 underscore 055101 had the highest effective in-spiral spin. We didn't see anything that definitively had a negative effective in-spiral spin, but GW190514065416 did have the most negative or smallest effective in-spiral spin, though it is still consistent with zero or positive effective spin. All right, next slide, please. Okay, just to dig into the spins a little bit more, we can actually look more closely at exactly what these spin vectors look like on the two merging objects. So each of these plots here shows the spins of the two colliding objects. The left-hand side of each circle is the spin magnitude and tilt of the primary mass, and the right-hand side is the magnitude and tilt of the spin of the secondary mass. So for 190412, for example, on the top left, you can see that there's this dark spot, and that corresponds to about 45 degrees, a tilt from the orbital angular momentum, and magnitude of about 0.4 for the primary mass. So that was one case where we made a very nice spin measurement of the primary mass. You can see the two disks in the bottom right have a very similar sort of thing happening where we're able to make that pretty tight measurement on the spins. The other cases that are shown in this plot are just examples where the effective in-spiral spin is large. All right, next slide, please. All right, so some people may be wondering whether there's precession in any of these systems. So there's a parameter that we look at called the effective precession spin parameter. This is essentially a measure of the spin in the orbital plane of the two objects. There's a few events where we actually see some difference between the posterior and prior for this chi-p parameter. So we've shown those in the plot on the right. The left-hand side of each of those violins is the posterior. The right-hand side of each violin is the prior. So for 190814 in particular, you can see a very strong constraint. And that just goes back to what I said before, where we know that 190814 has a primary spin that is very, very low. So that's forcing that chi-p to be very small. So we're not seeing precession in that system. In the other systems, and in particular 0412 and 0521, there's some mild hints of precession. We can't say for sure, there's no smoking gun evidence in any one of our events that there is precession, but these are two events where we're starting to see some hints of precession. And in particular, I do want to highlight that the population analysis of the entire catalog is seeing evidence for precession in the whole catalog. So we can't go on individual events and see precession, but on the population level we can. And you can hear more about that in the populations presentation in next week or so. All right, next slide. Okay, lastly, I just want to finish up by telling you about the 3D sky localizations. One of the most interesting things I think about this catalog is that we're seeing gravitational waves coming from much larger distances than we saw in 01 and 02, which is going to help to do studies of cosmology, for example. So we have a few sources that have estimated luminosity distances of about 5 gigaparsecs, which is about twice as far as the farthest event we saw in 01 and 02. 190814 was also an interesting event in this context because it had a very small sky localization. It was localized to about 19 square degrees on the sky, and the region of space that it was inferred to be in was about 3.2 times 10 to the minus 5 cubic gigaparsecs. So that's orders of magnitude smaller volume we've localized this event compared to many of the other events in the catalog. All right, and with that, I will hand it back to John.
John, you may want to check your sound.
Thank you. Sorry, I was saying I would like to finish with a couple of advertisements before the end of the presentation. So the first one is for the Astrophysical Implications companion paper. This will tell you a bit more about the whole population of sources that are out there, and you'll be able to find information about the merger rates, the cosmological merger rates, the distribution across the black hole mass, in particular, first evidence that we could be seeing something beyond the simple power law that we've been modeling before, and also, as Zohair was pointing out, statistical evidence for the orbital precession. So you can find much more information about that at the upcoming webinar that's devoted to this topic. I think that's the one that's happening in 1 week's time, but another advertisement will be put out for that closer to the time. And then there's the third of the series of webinars is devoted to tests of general relativity, where again, considering these events as a population is enabling us to get a much better leverage on some of the tests that we've been doing in the past. For example, we have tighter constraints on Lorentz violation, graviton mass, tests of gravitational wave polarization, and the parameterized post-Newtonian tests that we've previously published. There are several new things that we've been able to apply on this data set. We're looking at, for example, the properties of the post-merger object, and looking to see whether that is consistent with the masses of the objects that went into the merger, looking at the ring down of the black hole, and also testing for the presence of unexpected features such as echoes in the post-merger signal. So again, this you can ask many more questions and hear a lot more detail about this in 2 weeks' time at the third webinar. And then for those of you who want to get your hands on some of this data, some of these nice results that have been presented, I will point you towards the Gravitational Wave Open Science Center, where you can download the entirety of Gravitational Wave Transient Catalog 2. That's all of the events that have been presented to date. And there you can find the strain data, the actual waveforms that are coming out of the detectors, the detection statistics that Sarah has been talking about, those localization maps if you want to combine this with multi-messenger channels, and the parameter estimation samples for all of the different waveforms that Zohair has pointed out, as well as the combinations that we've been publishing in the paper. On top of that, there's some information that might be useful to those of you who are trying to reproduce plots in the paper. There are data behind the figures available for all of those, including the sensitivity injection set that was used to actually measure the sensitive volume of this run. So for the technically minded among you, I would invite you to go and download the data and start playing around with it. And I look forward to hear what's going to come out of that. So lastly, just to give you an overview of where we're going from here, there's still the remainder of O3, of course, to be published. That was the second 6-month period. As a reminder, we released 23 public alerts during that time period, but we would expect, again, with our offline pipelines to either confirm or disconfirm those, as well as to potentially increase that number still further. Looking further ahead to 04, well, our plans have been scuppered along with many people's by the pandemic, so there is probably going to be a slight delay in the start of the 4th observing run. But the good news is that KAGRA will be joining us for 04. This is the 4th detector in the network situated in Japan. Again, we will get to see how the sensitivity will compare to the other instruments, but this has the potential to much expand our localization capabilities in the future. So I'll finish up by thanking the audience for attending and apologizing for that technical glitch there when my broadband dropped out. But I would be happy now to turn over to the audience to see if there are any questions for our panelists that haven't already been answered in the chat. Thank you. Okay, so the only question I can see open at the moment is about the reference to the slides. It looks like that document has not yet gone live, so I'll make sure that that is made publicly available shortly after the recording. Other questions in the chat, people have been asking about the rates. Hopefully the information on the earlier slide will help answer that question if you're interested in the quantitative answer. If you're interested in the methodology, you'll better tune in for the populations webinar next week, where you can hear a lot more about how this was attained. Okay, so does anyone else have any questions? I might need to bring up my chat window. Okay, well, in that case, let me thank you all for attending once again, and I will hopefully see you in a week's time at the next webinar. Thanks very
John,
much.
we do have one question, I think, that just came in.
Oh, I'm sorry. So do you find it constrained Young's modulus for gravitational waves? Well, the Young's modulus for gravitational waves is, by analogy, a property of spacetime itself, and so that will be part of the test of GR in a sense, although I don't think it's phrased in quite that way, but I think you have the right idea. And I have a comment here from Nandita. Can we ask a few questions? Yes, please post your questions into the Q&A channel. The time scale for 04. So, as I said, it's likely that that will be delayed. Initially, we were hoping it would start at the start of next year. I don't think we're ready to commit to an answer, but the impression I get is that it's going to be probably as late as May or June next year, in the second quarter, if you like. Sorry, in 2022. Patrick's still here. He may want to give you a more official answer, but on the other hand, perhaps not. Okay, so there's a question coming in from Nandita. GW190814 is similar to GW190412. The difference of the masses emerging is large. The heavier object, inclusively a black hole, mass of 23 times the mass of the Sun. However, it is unclear whether the 2.6 solar mass object is a black hole or a neutron star. Yes, so this is a good question. I can direct you to Zohair to answer it if you would like to have a shout in.
Yeah, sure. I think your question is great, Nandita. I think people are generally puzzled about that 2.6 solar mass object because it does kind of seem right on the edge of what you might call a black hole or a neutron star. I think that many of the inferences on the maximum mass of the neutron stars puts that a little bit below the inferred mass of the secondary in 0814. But frankly, I think it's still an open question exactly what the secondary mass is, what kind of environment it formed in. That's an open question, and I'm hoping that more detections and maybe some things that look similar will help us to answer that question.
Thank you, Zohair. I hope that answers the question. Let's see. There's a question from Heisaka about the next webinar time. So there will be a different registration link sent around via the usual LIGO social media channels and the website. So there'll be a separate registration for that next week. So keep your eyes open. A further question about 190426. It has the lowest false alarm rate, and it has the highest false alarm rate. It has the lowest inverse false alarm rate. Probably neutron star black hole, but no EM counterpart detection possible. Any view? I guess you're asking us to speculate on this. Well, one thing that would be interesting, and you can find the details in the paper, is looking at the distance to this particular source. And I would suspect that you would have to consider exactly what model of a NSPH merger and the particular ejecta that would be produced by that to determine whether that lack of an EM detection is meaningful or not. But this is certainly one of the more tantalizing candidates that have turned up in the O3A analysis. And it's rather unfortunate that we can't say anything more definitive about it, but that's just the nature of the game. The detectors have still got a way to improve, and hopefully we will get our confirmed neutron star black hole signals before too long. That's my view. I think other people will have their own views, of course. If Zohair would like to say something, I think I can go ahead. He has mentioned something there.
Yeah, well, I don't think we've done this calculation in our paper, but you could, as John said, you could assume some model for the ejecta from this neutron, from a neutron star as it comes into the black hole. I think given that the black hole is a bit more massive than the neutron star in this case, assuming this is real, obviously, and the fact that we're not seeing some very strong spin in the system, that would make me think that you might not see any sort of EM counterpart, assuming this thing is real and you pointed at the right portion of the sky. But again, it's all model dependent, and I think there's a lot of work to still be done, and we're going to need more detections like this, and hopefully in much smaller sky localizations to help us answer this question.
Yes, that's a good point. The localization for this was terrible as well. Okay, are there any more questions? I don't see any. Oh, here's another one. Could you explain a little bit more about the gravitational wave polarization test? Well, I will defer to the testing GR presentation in 2 weeks' time. But in general, this is checking to see whether the two polarization states that gravitational waves have in general relativity can account for everything that we're seeing properly, or whether you would need to add more polarizations that might exist in alternative theories of gravity. That's really the lowest level of answer that I can give you here in detail. But I think the moderator for testing GR might be online, and I'm sure they will be taking notes for questions to answer in that seminar. Okay, I'll give people 30 seconds to ask any final questions, and then we can probably close the seminar there. Okay, well, I'd just like to finish by thanking you all for taking the time to attend and tune in on YouTube and on Zoom. And I look forward to seeing you at the next webinar in a week's time. Thank you.